Hi friends, today we'll discuss various possible solutions of one-dimensional wave equation, that is utt equal to c square uxx by the method of separation of variables. Consider the one-dimensional wave equation, that is dou to u by dou t square equal to c square dou to u by dou x square. Now let us take u equal to xt, where x as a function of x, t as a function of t, be the solution of PDE. Hence, the above equation becomes dou square of xt divided by dou t square equal to c square dou square of xt divided by dou x square. Here, the function is in terms of t, therefore x is a constant, we can take x outside, therefore x d square divided by d square t divided by dt square, because it is with respect to only one variable, therefore we can take it as a ODE. And here the RHS is the function of x, that is only variable x, therefore we can take t as a constant, therefore c square t into d square x by dx square. Now this is considered as ODE. Now dividing by c square xt on both sides of the equation, then we have, by dividing c square xt here, xx get cancelled, then we'll get 1 by c square t into d square t divided by dt square equal to, then in the RHS, dividing c square x t, then c square t get cancelled, we'll get 1 by x d2x by dx square. Now equating both sides to a common constant k, then we have, now we consider this as a first equation, therefore 1 by x d2x by dx square equal to k, and this is the second equation, 1 by c square t d2t by dt square equal to k. Now we take this into the RHS, multiply to the RHS, that is d2x by dx square equal to kx, d2t dt square equal to kc square t, and send it to the LHS, then we'll get d2x by dx square minus kx equal to 0, and d2t by dt square minus c square kt equal to 0. Here x is a common, I will take x common, and t by dx is a differential operator d, therefore I will take it as d square minus k x equal to 0, call this equation number 1. Similarly here t is a common, and take the differential operator d as a d by dt, therefore d square minus c square k t equal to 0, call this equation number 2. Now both are the homogeneous differential equation, it's a function of x and this is a function of t, therefore already we know the solution of homogeneous differential equation, that is complementary function itself is the solution, and depending upon this k value we have the different solution, therefore now we take k is a 0 and k is a positive and k is a negative, therefore first case we take k equal to 0, therefore above equations become, the first equation k is 0 means we'll get d square x equal to 0, and second equation k is 0 means d square t equal to 0. Then this is a homogeneous differential equation, therefore directly d replaced by m will get the auxiliary equation and leave the functions, that is x and t, will get m square equal to 0, and from the second m square equal to 0, and this is also from the second equation, that is also m square equal to 0, therefore if m square equal to 0, therefore the roots are m equal to 0 0, both the roots are same, that is roots are real and repeated. Therefore now the first solution of the first equation, that is in terms of x, therefore x equal to, if the roots are repeated, therefore we can write it as c1 plus c2x into e to the power root into x. Root is repeated, therefore 0, 0 into x. And second equation, that is in terms of t, therefore t equal to, and we take other constants, therefore c3 plus c4t into e to the power root into t, that is 0 into t. And it becomes, therefore x equal to c1 plus c2x, e to the power 0 is 1, therefore c1 plus c2x is the solution, and t equal to c3 plus c4t, this 0 e to the power 0 is 1, therefore c3 plus c4t. Hence, the solution of the PDE when the constant is 0 is given by u, that is xt, which is equal to multiplication of x and t, that is c1 plus c2x into c3 plus c4t. Now we consider the second case, that is positive. We can take k as a p square. Then equation number 1 and 2 become d square minus p square x, and second equation d square minus c square p square t equal to 0. Then from the first equation we can take auxiliary equation replacing d by m, that is m square minus p square equal to 0, and from the second equation again replace d by m, auxiliary equation have m square minus c square p square equal to 0. Here m square equal to p square, therefore our roots are m equal to plus or minus p, and in the second, from the second equation m square equal to c square p square, which implies our roots are m equal to plus or minus cp. Here both the roots are real and unequal, therefore from the solution for the first equation x equal to c1 e to the power first root, that is positive root px plus c2 into e to the power minus second root, that is minus p into x. And second equation, the solution of second equation, it is in terms of t, therefore t equal to, we can take other constants c3, the e into e to the power first root, that is cpt plus c4 e to the power second root, that is minus cp into t, because it is a function of t. Therefore we have, hence the solution of PDE when the constant is positive is given by u equal to, that is xt, which implies c1 dash, we can take the constants instead of c1 to c4, now take it as c1 dash e to the power px plus c2 dash e to the power minus px into c3 dash e to the power cpt plus c4 dash e to the power minus cpt. Now consider the third case, that is k is a negative minus p square. Then the equation number 1 and 2 become d square plus p square into x equal to 0, and the second equation becomes d square plus c square p square t equal to 0. Then the auxiliary equations become d replaced by m, therefore m square plus p square equal to 0, and second equation m square plus c square p square equal to 0. Then we have m square equal to minus p square, m square equal to minus c square p square. Then you will get the complex roots, the two purely imaginary numbers, therefore m equal to plus or minus pi and m equal to plus or minus cpi. If we have purely imaginary roots, directly it is in terms of cos and sin. Therefore from the first equation we have the solution is in terms of x, therefore x equal to c1 cos px plus c2 sin px, and from the second equation it is in terms of t, therefore t equal to c3 cos cpt plus c4 sin cpt. Hence the solution of PDE when the constant is negative is given by u equal to, that is xt equal to, now we replace by c1 to c4 constant by other constant, that is c1 double dash cos px plus c2 double dash sin px into c3 double dash cos cpt plus c4 double dash sin cpt. All these three cases use the various possible solution for the one-dimensional wave equation. Now we consider the various possible solutions of the one-dimensional heat equation, that is ut equal to c square uxx, by the method of separation of variables. Consider the one-dimensional heat equation dou u by dou t equal to c square dou 2u by dou x square. Let us consider u equal to xt, where x equal to function of x and t equal to function of t be the solution of PDE. Hence, the above equation becomes dou of xt by dou t equal to c square dou square of xt by dou x square. And here LHS is a function of t only and RHS is the function of x only. Now here x is a constant and here t is a constant, therefore we can treat it as ODE. Therefore take x as a constant, then it is dt by dt equal to here function of x only, therefore take t as a constant, therefore c square t d2x by dx square. Here also we can divide by c square xt on both sides, then xx get cancel, will get 1 by c square t dt by dt equal to here c square t get cancel 1 by x d2x by dx square, that is divide c square xt on both sides. Now equating both sides to a common constant k, then we have 1 by c square t dt by dt equal to k, and the other equation 1 by x d2x by dx square equal to k. Now send this denominator term to the RHS, therefore dt by dt equal to k c square t, and send this denominator x to the RHS, therefore d2x by dx square equal to kx, and send it to the LHS, will get dt by dt minus c square kt equal to 0, and d2x by dx square minus kx equal to 0. Here t is a common, will take differential operator d by dt as a capital D, therefore d minus c square k t equal to 0, call equation number 1. Now here x is a common and d by dx is a differential operator d, therefore d square minus k into x equal to 0, call this equation number 2. Here also we have the homogeneous differential equation, and by assuming a different k value we will get a different solution using homogeneous differential equation. Now consider case 1, that is take k equal to 0, then equation number 1 and 2 become dt equal to 0, and second equation becomes d square x equal to 0. These are the homogeneous differential equation, therefore by taking the auxiliary equation we will get the solutions, and d replaced by m, therefore m equal to 0, here m square equal to 0, therefore m equal to 0 means only one root, therefore solution of it is in terms of t, therefore t equal to c1 e to the power root into t itself is c1, and from the second equation we have two roots, therefore x equal to the two repeated roots, therefore c2 plus c3x into e to the power 0x, therefore c2 plus c3x. Hence the solution of PDE when the constant is 0 is given by u equal to xt, therefore c1 into c2 plus c3x, or u of xt equal to a plus bx, where a is c1 c2 and b is c1 c3. Now consider the second case, that is k equal to positive, then the equation number 1 and 2 become d minus c square p square t equal to 0, the second equation becomes d square minus p square x equal to 0. Now our auxiliary equation becomes m minus c square p square equal to 0, and the second equation m square minus p square equal to 0. Now m equal to c square p square, this is only one root, and from the second equation m equal to plus or minus p are the two roots. Then the solution for the first equation, it is in terms of t, therefore t equal to c1 dash, because we can take different constants from the previous, therefore c1 dash e to the power the root c square p square t. And now the second equation is in terms of x, therefore the two roots, the two different roots, therefore c2 dash, the first root p, therefore e to the power px, plus c3 dash, the second root minus p, therefore e to the power minus px. Hence the solution of the given PDE when k is positive is given by u equal to xt. Therefore c1 dash e to the power c square p square t into c2 dash e to the power px plus c3 dash e to the power minus px, or u of xt is given by e to the power c square p square t. I will take outside, then multiply c1 dash to the inside, that is c1 dash into c2 dash, I can call it as a dash, and c1 dash and c3 dash, I can call it as b dash. Therefore a dash e to the power px plus b dash e to the power minus px, where a dash is c1 dash c2 dash and b dash is c1 dash c3 dash. Now consider the third case when k is negative, that is k equal to minus p square. Therefore equation number 1 and 2 become, therefore equation number 1 becomes d plus c square p square t equal to 0, and the second equation d square plus p square into x equal to 0. Therefore now we get the auxiliary equation replacing d by m, therefore m plus c square p square equal to 0, and from the second equation m square plus p square equal to 0. Now from the first equation m equal to minus c square p square is the only one root, but from the second equation m square equal to minus p square, therefore we will get the complex root, that too purely imaginary, m equal to plus or minus pi. Therefore the solution of the first equation, that is in terms of t equal to only one root, therefore t equal to c1 double dash e to the power minus c square p square t, and the solution of second equation, it is in terms of x, and that too purely imaginary, therefore it is in terms of cos and sine in terms of x, therefore c2 double dash cos px plus c3 double dash sine px. Hence the solution of the given PDE when k is negative is given by u equal to xt, that is c1 double dash e to the power minus c square p square t into c2 double dash cos px plus c3 double dash sin px, or u of xt is given by, now I will take this is outside and I will multiply c1 double dash to inside, therefore c square minus c e to the power minus c square p square t, c1 double dash into c2 double dash, I can call it as a double dash cos px plus c1 double dash into c3 double dash, I can call it as b double dash sin px, that is where a double dash is c1 double dash c2 double dash and b double dash is c1 double dash and c3 double dash. These are the three cases for the various possible solution the one-dimensional heat equation.